Alright, exercise 27. This one's a long one, so let's hope that my computer doesn't break. So we're going to start with part A. There's parts A through E, and put them all on separate pages. So anyways, we're going to do part A. Negative infinity less than x1 less than xn equals x. Where x is just some number, some real number. Then, so here I've got some more space here, so let's write this out. Sum from 1 to n of fxi. We'll stick with I. It's fxi minus 1. What is this equal to? This is just a sum of, well, f is increasing, so we can just remove the absolute values. But then by telescoping, this is f of x minus f of x0. So then t of f of x is the supremum over all such partitions of this value. But really the only thing that's going to vary here is this value of x naught. So it's a supremum over all x naught. And in any partition, x naught is going to be strictly less than x. And that's really all we know. So it's a supremum over all x naught less than x of f of x minus f of x0. But since, and yeah, it's a supremum, yeah, however you want to write it. But anyways, f is increasing, and so the supremum of these things is going to be attained when we minimize the value of f of x naught. And that's going to happen when we look at f of x minus infinity. And so that proves this parenthetical part. And I think that's why it was parenthetical, is because you use it along the way. So if f is bounded by, say, m, then tfx is, let's see here, well, this is just f of x minus f of minus infinity, and certainly we can bound this by 2m. But this holds for all x in R, so taking the limit as x goes to infinity, this is going to be less than or equal to 2m, which is less than or equal, which is strictly finite. Hence, f is in BV, because that's what it means. Alright, there's one. Now for this one, linearity. Let's just say let f, g, a, b as above. Then t of af plus b. Yeah, let's write this out a little more. taf plus bg. It's a lot. So for all x and r, this is going to be equal to the supremum overall sum from 1 to n of af xi minus fxi minus, nope, no, we're not there yet. This is plus b gxi, and now we subtract the afi minus 1 plus b gxi minus 1. And this thing here, this condition, I'm just going to put a dot here. I mean, it's the same thing we've been doing in this whole section where we take partitions from negative infinity to x. And so anyways, so what's this? This is going to be less than or equal to, well, if we combine the like terms of the f's and the g's in here and use the triangle inequality, this is less than or equal to the sup for 1 over n of afxi plus bg. Nope, now we're moving on. God, I got those two lines flipped. Anyways, plus, and then, actually, you know what, we can just do this in one step. What's going to happen when we're looking at this is that this a is going to pop out here in absolute value. We're going to get the sum from 1 to n of just the absolute value of fxi minus fxi minus 1. And likewise, we're going to get plus b, sum from 1 to n of gxi minus gxi minus 1. Right? And then this is just going to be the dot thing again, so overall such partitions. But then if we break this up and consider the supremum of these and the supremum of these separately, then any cancellation that possibly could have occurred between the two terms in this thing is removed. Though now that I think about it, because this is all absolute values, it might be strict equality, but I'm an analyst, so I don't care. Less than or equals 2 is the only thing that I really need here. Bring the a out and we get the sup 1 to n of fxi minus fxi minus 1, such that whatever, then this is plus b of the sup of all such sums, g, come on, fit gxi minus 1. Such that, yes. Okay. But then what is this? This is just a times tfx plus b times tgx. Now f and g are in b. F, g, and bv. So f is bounded by, say, let's call it mf, and g by mg. So then TAF plus BG x is less than or equal to A MF plus B MG. So then the limit as x goes to infinity of TAF plus BG x is also going to be less than or equal to AMF BMG. This is finite, so AF plus BG is in BV. And there we go. Alright, my computer is not on fire yet. Let's see if that continues. Okay, so we want F to be in BV here, and so I'm gonna just take any A and B and R. We're going to assume that A is strictly less than B, and xy in this closed interval. If f prime is bounded by m, I'm not saying like if f prime happens to be bounded, I'm saying f prime is definitely bounded, and if we say that m is the particular bound for f prime, then by the mean value theorem, there is some c in this open interval from x to y such that f of y minus f of x over y minus x is equal to f prime of c. But f prime is bounded by m, so this is less than or equal to m. But note that this holds, so this step here was just kind of an intermediate step to get that this ratio is bounded by m, and this holds for all x and y in this closed interval. So then for all a equal to x1 less than, this is another partition, we have, what do we have? Sum from 1 to n fxi minus fxi minus 1. This is bounded by, well, here, let's write out some more details. Just by this thing that we did before, if we were to bring this y minus x over to the other side, then it would come over here. So this is just mxi minus xi minus 1. And then this is just equal to, you bring the m out front. So this is m times the sum from 1 to n of xi minus xi minus 1. But of course, let's see here. This is xi is greater than xi minus 1. So again, this is equal to sum 1 to n. Guess I could have combined some of these steps, but oh well, I didn't. Then this is of course telescoping again. So what we're going to end up with is m of b minus a. And this is less than infinity. Hence, f is in bv a b. Alright, so that takes care of c. Now let's do this. Let f of x equal sine x. F is differentiable on R, and f prime equals, well, what's the derivative of sine? It's cosine. But this is bounded on R. So by part C, which we just did, we know that for all A and B and R, F must be in BV AB. So that's that part. However, let xk equal k pi over n for k in the natural numbers. This does not include 0. Then for all, let's say, n in the natural numbers, we have the sum from 1 to n of, nope, this is not going to be a long string of computations. This is going to be here. And for all n and n, what are we going to say here? What's the best way to say this? So the best way to say this is that for all n and n, actually no, this should include 0 because we want 0 to be one of these. So this is going to be for k and omega, which is just finite ordinals, which is just the natural numbers including 0. It's not very standard, but I like it as a way so that you can write omega when you want 0 and n if you don't want 0. So then for all n in the natural numbers, not in omega, 1 of sine xn and sine xn minus 1 will be plus or minus 1, and the other will be 0. That's because if you look at this unit circle, we're taking k pi over 2 for integers which are not negative. So we're going to start at 0, then so we're going to start at this point, and here the y-coordinate is 0, so sine is 0, then 1, 0, minus 1, 0, 1, 0, minus 1. We're going to keep going around as we keep going. And so if you pick any two adjacent ones, like xn and xn minus 1, one will be on the x-axis, and one will be either at the top or bottom here. And so basically that's why I'm saying that one of these two values will be plus or minus 1 and the other will be 0. So then, see here. So sum from 1 to n of sine xi minus sine xi minus 1 is going to equal n. Because we're taking n of these, and we just proved that each one of these things on the inside is going to be plus or minus 1. And so, let's see here. So this means that Tf of n pi over 2 minus Tf0, well, this is just a supremum over all such sums of this form. And so it's certainly going to be greater than or equal to n. And so one way, if we wanted to move the Tf0 over to the other side. Oh, wait a minute. Can we do this? Yeah, we're allowed to do this. We have to be careful, because we don't want to be writing infinity minus infinity. And I think that this is writing infinity minus infinity. So let's try to write this in a different way where we're not writing infinity minus infinity. So how are we going to approach this? This is actually kind of tricky. Actually, this is okay, because what we can do from here is that we can, so limit as n goes to infinity of the sum from 1 to n of sine xi minus sine xi minus 1, this is equal to infinity. And so what does that tell us? Where are x and x naught? So, so what does this tell us? Okay, here's what we're going to do. Here's what we're going to do. I found the solution. What we're going to do is going to let xk equal negative k pi over 2 for k and omega. Then all of this stuff still holds. Limit as n goes to infinity, this is equal to 0. So, but what's the first value here? The first value here is 0. So what this says is that Tf of 0 equals infinity. Right? Because Tf0 is the supremum over all such partitions. And we've just shown that you can construct partitions by taking n to infinity. You can get partitions which result in a sum that's arbitrarily large. And so, but this is just a particular way to take the supremum. But that doesn't matter, because even if you were to take the supremum, take any other partition, you can't improve upon an estimate that gives you positive infinity. And so basically what this tells us is that Tf of 0 is equal to infinity. But thus, f cannot be in bounded variation. Because if it were in bounded variation, then the limit as x goes to infinity of tfx would have to be finite. But we know that tf0 is infinity at, we know that tf is infinity at 0, and tf is an increasing function. And so it's, so let's write this out. So tf equals 0, since tf is increasing, tf infinity equals 0. No. TF infinity equals infinity. Hence, hence, f is not in bounded variation of AB. Oh, wait, bounded variation of AB. No, not in bounded variation. That's right. F is not in bounded variation. Okay. After going through this, I want to go back and check on part E, so I'm going to pause this and then come back to it. So in the last part, I guess I was a little bit confused on how you define the total variation of a function over a closed interval. It's defined by the supremum of the partial sums given partitions over that interval. But if the function happens to be of bounded variation, you can define it as the difference between tf of the one endpoint minus tf of the first endpoint. But that's, if the function is not of bounded variation, you can't define that, because that might be infinity minus infinity, and that's not well defined. So that's the issue I ran into there. But thankfully, in this next part, we can get around that. So let's look at the case of a less than or equal to 0 less than b. Now, if you think about this, what does x looks like this, and sine looks like this or whatever. Basically, these are both odd functions, and an odd function times an odd function is an even function. And so we get symmetry, we get reflective symmetry across the y-axis. So it's going to look something like, I don't know, maybe like this and this. But it's going to be like reflective across here. And anyways, the point is that if we prove it for one of these intervals, then it looks exactly the same reflected, and so you basically can just say, like, by symmetry, this the result holds for the other interval. So we're just going to look at if a is less than or equal to 0 is strictly less than b. And of course, all that really matters is that 0 is contained in this half-open interval. So anyways, let's get going. So let xk equal 2 over k pi for k in. And now this time, I want to make it the natural numbers. I really don't want to have 0 in here. So anyways, choose n1 in n large enough that xn1 is less than b. Because we want to get, what we really want is we want a partition of the interval from 0 to b. Okay, so we've got this. Then for all I greater than n1, fxi minus fxi minus 1 is greater than or equal to, now let's stick with this, 2 over I pi. And because this is real analysis, I hope you trust me when I'm saying that this is not the imaginary number. This is just an index this could be potentially confusing, especially since we've got sines involved, but I don't think it'll be too much of a problem. I don't want to go back and completely rechange my notation. Anyway, so this is sense. This is kind of like what happened in the previous case, but we have to be a little bit careful here because we have this greater than equal to rather than equal to. And the reason is that either fxi equals 2 over I pi times plus or minus 1, and f of xi minus 1 equals 0, or f of xi is equal to 0, and f of xi minus 1 is equal to 2 over I minus 1 pi times plus or minus 1. So if we take the absolute value of this difference, what we're just going to get is this or this in absolute value. And since we're taking the absolute value, the plus or minus 1 is going to drop out. And dividing by, now let's see here now. If we're dividing by I minus 1, then you're dividing by a smaller number. And so the result's going to be bigger. So, right, this is going to be greater than or equal to the max of these two, but this one's always smaller. So if we want to make sure that this estimate always holds, then we got to make it greater than or equal to 2 over I pi. But that's going to be a good enough of an approximation because this 2 over I, we're going to get a harmonic series. So anyways, so for all n2 greater than n1 plus 1, the sum from n1 plus 1 to n2 of fxi minus fxi minus 1 is going to be greater than or equal to the sum from n1 plus 1 over n2, 2 over I pi. Also, a is going to be less than or equal to 0, which is less than x and 2, which is less than x and 2 minus 1, which is less than all the way up through x and 1, which is less than b. So this is a little bit of a backwards indexing from how we usually do partitions, but I mean, it's whatever. It works. So now as n2 goes to infinity, the sum diverges. So the supremum overall, I'm going to write this out just so that's very clear. So the supremum overall from 1 to n of fxi minus fxi minus 1 such that a is less than or equal to x0, or no, we do a equals x0 is less than all the way up through xn is equal to b. This is going to be greater than or equal to a less restrictive supremum, which is just a supremum from, say, n1 through n plus n2 of f of xj minus fxi minus 1, where here's where we have the less restrictive condition. We've got the 0 is less than x and 2 less than all the way up through x and 1 is less than b. But the supremum, as we just found out, this goes to infinity as n2 goes to infinity, so this is just infinity. And so then this supremum here, this original supremum, is infinite. But this supremum is what we mean when we refer to the total variation of f on the closed interval from a to b. And so hence, this means by definition that f is not in bounded variation from a to b. And this completes the proof, because we've taken care of the symmetric case by our argument at the beginning.